Hi everyone. So this is a video illustrating how to balance redox reactions. So there, thankfully or not thankfully, depending on your perspective, is a prescribed method for balancing all redox reactions. It's a bit involved, but if you follow this set of steps, then you should automatically balance it every single time. It's complicated a little bit because a lot of these reactions, a lot of these redox reactions occur in solution where there's hydronium ions and hydroxide ions around, which are capable of also donating and providing electrons and participating in the reaction. So balancing redox reactions is complicated by the fact that it's slightly different depending on whether you do it in an acidic or basic solution. But the key principle here is that you start usually with some unbalanced chemical reaction, and the first thing you'll need to do is to split it into its separate half reactions. Figure out which one is being oxidized, which one is being reduced. And that can be a little tricky sometimes, but yeah, we'll start there. And then essentially you balance each of those half reactions individually. So again, there is a specific method for doing that. You first, by making sure that all the different atoms are balanced. The balanced chemical equation should have the same number of elements on each side of the equation. It's a little complicated in the sense that we're going to start by balancing everything except for hydrogen and oxygen. And then we balance oxygens by adding waters. So we'll add oxygen by adding an H2O. In the act of adding H2O, we've also added hydrogens to our equation. So then we go back and we add hydrogens to the opposite side of the equation to balance out the hydrogens that we just added from the water. And then lastly, since a redox reaction involves transfer of electrons, and you have not only conservation of mass, conservation of the atoms, you also have conservation of charge. So you need to balance the electrons you need to balance the charge by adding electrons to each of your half reactions. And then, since we again want to make sure we're transferring the correct number of electrons, you don't always, but you might need to multiply your half reactions by an integer number, by a factor, in order to make sure you're adding the same number of electrons. And then finally, here at the end, you finally add together your two half reactions and then cancel out anything that's the same on both sides of the reactions. And if you're doing a redox reaction in an acidic solution, at that point you would be done. If it's occurring in a basic solution, then there's one more step here, which is that you cancel out the hydrogens that would have been present in an acidic solution. You cancel them out by adding hydroxide ions to both sides of the equation, one of them for every hydrogen. Then you assume those hydrogen ions combine with the hydroxide ions to produce water, and then, just like you did up here with step 7, you cancel out any extra waters that you have on both sides of the equations. So that's a lot of rules to memorize, certainly. And some of them are going to seem a little strange without an example. So best way to do this is with an example. So I've got 3 examples that I was going to work through. Again, it's an algorithm. You'll see that we frequently will end up doing almost the exact same thing every single time. So here is a reaction that I would like to balance, which is the reaction between methanol and the dichromate ion, Cr2O7 2-, reacting to form formaldehyde, CH2O, plus the chromium 3+ ion. So this might be step 1 here, just writing out the unbalanced reaction. And now I need to identify the two half reactions, what's being oxidized and what's being reduced. So carbon here, carbon is going from carbon in methanol to carbon in formaldehyde. So I will write that as one of my reactions. So I have CH3OH going to CH2O, and then I have dichromate going to chromium 3 plus. So it might not be obvious here, but this step is the reduction half reaction, and this is the oxidation half reaction. I can illustrate that to you. If you've seen my video on how to identify oxidation states, the oxygen here, those should all have a -2 charge. There are 7 of them. And then the molecule, or rather the ion, has a net -2 charge. So these guys, they have a net charge of -14. And then there are 2 chromiums. The only way I can get to a net negative charge of -2 if I'm adding over 14. So I've got 2 times some unknown value. That should be equal to +12, which means that the charge, or rather the oxidation state of chromium, has to be +6. So it's going from its +6 oxidation state down to its +3 oxidation state. So this is necessarily the reduction step, and this is the oxidation step, if we are curious about that distinction. We don't necessarily need to know that for balancing the reactions, but it's nice to sort of keep track of that and make sure things make sense as they should. Okay, so then step 3 says balance all of the atoms except for hydrogen and oxygen. So for my first half reaction, okay, hydrogen, oxygens, we're going to balance them, or we're going to balance them later. We don't have to worry about them yet, but the carbons we need to balance, except that they're already balanced. 1 carbon, 1 carbon. So I'll leave that alone. CH3OH going to CH2O. The dichromate, I start with 2 chromiums, end with only 1, so I've got to multiply this by a factor of 2. So I've got chromium 2O7 2 minus, converting into 2 chromium 3 plus ions. And now we're into step 4 here, which says balance these reactions by adding water to balance the oxygens. So first reaction has 1 oxygen as a reactant in the reactants and 1 oxygen in the products. So I don't need to add anything here to balance oxygens. Those are already balanced. But then it says add hydrogens, or rather H plus ions, to balance the hydrogens. So I have 4 hydrogens over here, only 2 over here. So I need to add 2 hydronium ions, or just H plus ions over there. In this half reaction, I have 7 oxygen atoms, none over here, so I need to add 7 water molecules. Now the oxygens are balanced, but by doing so, I've added a bunch of hydrogens. I've added 14 hydrogens over here, and I don't have any hydrogens over here. So to balance the hydrogens, I will add 14 H plus ions. Now in step 5, I apologize, I'm gonna run out of space very quickly here, so I'm not gonna keep labeling each of these steps. But I'm on step 5 right now. Step 5 says to balance the charge on both sides of the equation by adding adding a necessary number of electrons. So this side of this equation has a net charge of 0. This side of the equation has a net charge of +2. The only way I can balance these charges, again, over here the net charge is 0, over here the net charge is +2. The only way I can make 0 equal +2 by adding electrons is if I add 2 negative charges. And then that would get me to a net charge of 0. So that means I need to add 2 electrons to this side of this equation. Over here, I've got a net charge of +6. And over here, I have 14 minus 2, so I have a net charge of +12. The only way I can get these to equal is if I add 6 negative charges to this side. -6 plus 12 will give me +6, and then everything will be equal. So that's when I can add, or that's when I should add 6 electrons to this side of the equation. All right, so now I'm down to step 5, or rather I'm done with step 5. Step 6 says if you need to multiply both of the reactions to make sure you're transferring the same number of electrons. Here carbon should be losing electrons and the chromate ends up gaining the electrons. So there needs to be balance of electrons. I got 6 electrons being gained here, but I'm only generating or providing 2 electrons in my oxidation step. So I need to multiply this through by 3, multiply everything in here by 3, and that will get me 6 electrons over here. Now I've got the same number of electrons, and then my last step is step 7, which says to add together these 2 reactions and then cancel out any similar species. So I'm going to try to write this all on one line or close to one line. I doubt I'll be able to, but I'll do my best. So I have 3 methanol molecules, 3CH3OH, plus 6 electrons, plus 14 hydrogens, plus the dichromate ion. That goes into 3 formaldehyde molecules, plus 3 H plus ions. Actually, let me make sure I got that right. No, that should be 6 H plus ions. I wonder why that looked strange. Sorry, I apologize. I screwed up when I was doing my multiplication. So that should be 6. Okay, so 3 methanol molecules, 6 hydrogens, 6 electrons, 2 Cr3 plus ions, and 7 water molecules. So let me cancel out any species that are the same. So these electrons, they're on both sides of the equation, so those electrons cancel each other. There's no methanols on that side, so that doesn't cancel. Hydrogens, I've got 14 hydrogens over here, and I end with 6 hydrogens. So the net change here, I end with 6 hydrogens. I should have started with more than 6 hydrogens. So the net change here is 6 of these hydrogens don't do anything. So I start with 14, but 6 of them are left over. So I really only have a change here in terms of 8 hydrogen atoms. That's the net change in terms of the number of hydrogen ions. And then the dichromate ion is left alone. There's no water molecules on this side, so everything is done. So let me write out the balanced reaction that we have at this point. I'm going to copy that up here. So this is the net reaction we have so far. This is in acidic solution. So that's going to be 3CH3OH plus the dichromate ion plus 8 H plus ions goes to, I'm going to run out of space again, goes to 3 CH2O molecules plus 2 chromium 3 ions plus 7 water molecules. This is my balanced chemical reaction if it were to occur in acidic solution. But if it were actually occurring in basic solution, we can still work with this. We just need to alter it a little bit. So if we're doing it in basic solution, it says to add hydroxide ions to both sides, 1 for every hydrogen ion, and then cancel any water molecules that you form as a result. So let me illustrate how that works. So I've said that this is going to continue here. This converts into this. I've got 8 hydronium ions here, so I need to add 8 hydroxide ions. And since I want to make sure everything is balanced, I'm going to add 8 hydroxide ions over here. I can't just out of nowhere add 8 hydroxides without adding them to both sides. That would unbalance my equation. And then we'll say, okay, these 8 hydronium ions should react with these 8 hydroxide ions, and they should give me 8 water molecules. And then we would want to cancel any additional hydrogen, any water molecules, any excess water molecules. So I start with 8 water molecules, I end with 7 water molecules. These 7 water molecules didn't do anything. So I'll cancel them out, and I'll cancel out 8 of the hydrogen, or rather 7 of the hydrogen, 7 of the water molecules, and I'll be left with this. So then my balanced chemical equation in basic solution is this: 3CH3OH plus the dichromate ion plus that one remaining water molecule turns into 3 methanol molecules plus 2 chromium-3 ions plus 8 hydroxide ions. So that was the balanced chemical equation if I did it in basic solution, and if I did it in acidic solution, it would have been this reaction. So I would have been left here with my 8, oh, and I gotta get rid of these hydroxide ions I added. And then I've got this. So these are my 2 balanced redox reactions between methanol and dichromate, whether it's happening in acidic conditions or whether it's happening in basic conditions. So, admittedly, that was a lot to work through, but I will guarantee every other example you do is essentially going to follow the same set of manipulations, more or less. So let me do a couple more examples of this. So let's do this example, which is between the manganate, or is that permanganate? I think it might be the permanganate ion, and the iron 2 ion, converting into manganese 2 plus and iron 3 plus. So this is my unbalanced reaction. First thing to do is to split this into 2 half reactions. So I have manganese, or rather the permanganate ion, converting into Mn2 plus, and I have the Fe2 plus converting into Fe3 minus. Now I want to balance all atoms except for hydrogen and oxygen. So I've got 1 manganese atom here, 1 manganese atom there, so those are balanced. 1 iron atom here, 1 iron there, those are balanced. So step 3 is unnecessary. Great. Step 4, balance the oxygens by adding water, and then balance the hydrogens by adding H+. So I've got 4 oxygens over here. I'll need to add 4 oxygens in the form of water over there. And then if I want to balance the hydrogens that I just added, I will add, well, there's actually 8 hydrogens here, so I will add 8 hydrogen ions over there. This reaction, no oxygens to balance, it's done, and no hydrogens to balance, it's done. So now we're going on to step 5. Add electrons to make sure that the half reactions are balanced. So let's see here. Over here, my net charge is, what is this? +7. Over here, the net charge is +2. So the only way I can make +7 equal +2 by adding negative charges is if I add 5 negative charges over here. That will give me a net charge on this side of plus 2. So let me move this around actually just a little bit. So this is, I was going to add 5 electrons to this half reaction. So now I have plus 8, minus 1 is plus 7, minus 5 gives me plus 2. So there's my plus 2 for my total charge on this side. And then on this side I've got a 2 plus from the manganese. So yeah, now those are balanced. Over here I've got 2 plus on this side. And on this side I've got 3 plus. The only way for these to be equal is if I add one more negative charge over here. So this is just going to have a single electron being added to balance out that reaction. So here we can now visualize, if you hadn't labeled them as such before, this must be the oxidation half reaction because the iron is losing an electron. The manganese, this must be the reduction reaction because the manganese is gaining these 5 electrons when it becomes the Mn2 plus ion. So this is the reduction step, this is the oxidation step. Okay, so we're through step 5 here. Charges are balanced. If you need to, multiply the reaction by a factor to ensure the same number of electrons are transferred. So manganese is gaining 5 electrons here. We're only able to get 1 electron out of iron, so I need to multiply this whole reaction by 5. That'll give me those 5 electrons, and then step 7 here is to finally add everything together to get my net equation. So I should have 5 iron 2 plus atoms, or ions I should say, manganese, the permanganate ion, plus your 8 hydrogen ions, converting into 5 iron 3 plus ions, plus the Mn2 plus 4 water molecules, and we can already, I didn't write them up here, but you can see I've got 5 electrons on my reactant side, 5 electrons on my product side. Those are going to cancel out by design. So this is, let me see here, I need to cancel, I need to be special, cancel any species that appear on both sides. Iron 2 plus, it's not over there. Permanganate, it's not over there. Hydrogen plus ions, not over there. Alright, so that last step is unnecessary. I don't need to cancel anything. Alright, this is the reaction that you would have if it were in acidic conditions. And so we would be done if I was just trying to balance this chemical, this redox reaction in acidic solution. In basic solution, we continue on to figure out what it is in basic solution by adding hydroxide ions to turn these hydronium ions into water molecules. Again, I'm sorry, not hydronium ions, hydrogen ions. So the way we'll do that is we'll have the 5 Fe2 plus the Mn O4 2 minus plus 8 H plus, and then I was going to add 8 hydroxide ions there. Then I get my 5 Fe3 ions, my Mn2 plus ions, 4 H2Os, and again I had just added 8 hydroxide ions, so I will add 8 hydroxide ions to that side. Then we'll assert that these 8 hydrogen ions and the 8 hydroxide ions, those combine to make 8 water molecules. And now I'm starting with 8 water molecules. I end up with 4 left over, so my net change here is that I should lose only 4 water molecules. So my net balanced reaction here, if this is going to occur in basic solution, is that I have these 4 water molecules remaining, and if I was going to make this just a little bit neater, I'd bring those hydroxide ions, 8 hydroxide ions. So this again is the balanced chemical reaction if it's occurring in acidic solution, and this is the balanced chemical reaction if it's occurring in basic solution. So again, I essentially just followed the exact same algorithm. There's the exact same set of steps. A few of them didn't need to be done. Like for instance, for the iron, I didn't have to add any hydrogens or oxygens, but we still check that as though we might needed to have done that. That's a one. Anyway, one last example here I will do. All right, so this one is a little strange. This is a very a special type of redox reaction. It's called a disproportionation reaction. It's special in that chlorine is serving both as the reducing agent and as the oxidizing agent. And it ends up being both oxidized and reduced during the course of this reaction, as I'll illustrate here in just a second. But this is my unbalanced reaction, but my two half reactions here are going to be chlorine converting into chloride. So that's one reaction. Or chlorine converting into hypochlorite. So this here, these are my two half reactions. Okay, so let's work our way through this. Step 3 here, balance all of the atoms except for hydrogen and oxygen. So I've got 2 chlorines over here, only 1 there, so I'll balance that. 2 chlorines here, only 1 there, balance that, okay. Add water to balance oxygens, then add hydrogen ions to balance hydrogen. Don't need to do that here. I do need to do that here. I've got 2 oxygens over there, so I'll add 2 water molecules over here. Now I've added 4 hydrogens, so I will balance that out by adding 4 hydrogen ions. So that's step 4. Step 5, add electrons to balance the charge. So over here I have a net charge of 2 minus. So I've got a net charge of 2 minus over here and a net charge of 0 over here. So I'm going to add 2 electrons in order to balance out the charge, make sure everything has a net -2 charge. Over here I have 2 negative charges from the hypochlorite and then 4 from the hydrogens. So I have a net charge here of +2. The only way to get that to equal the charge over here, which is 0, is if I add 2 negative charges. So I will add 2 electrons to my products in order to balance the charges. Alright, so now that's done. Step 6, if we need to, multiply to make sure that we're transferring the same number of electrons in my redox and my reduction and my oxidation steps. So I'm gaining 2 electrons from the chlorine in this step, and over here I'm losing 2 electrons from the chlorine, so number of electrons is balanced, so step 6 here is unnecessary. So then step 7 says to add the 2 half reactions together, so let's do that, and then cancel any unnecessary species. So these 2 electrons, those are immediately going to cancel, so I'm just going to deal with the atoms, or the atoms and the ions and the molecules that we need to deal to, because we've specifically made sure that these electrons are going to cancel. So I've got 2 chlorine molecules plus 2 water molecules going to 2 chloride ions plus 2 hypochlorite ions plus, I can put this over here, plus 4 H plus ions. And technically this reaction is now balanced in acidic solution because I have the correct number of chlorines. I got 4 chlorines here, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2 oxygens, 1, 2 oxygens, no charge over here, 1, 2, 3, 4 negative charges, plus the 4 positive charges, net 0 charge. So this is balanced in terms of number of atoms and total charge. But I would not say this is the best representation of this, because if you check all of the molar coefficients, they all share a common denominator of 2. So I can cancel some of these species out. So I can simplify this reaction just by dividing everything here by 2. So I get the chlorine, the water, the chloride, the hypochlorite, and only 2 H plus ions need to participate in this net balance reaction. So this is the balance reaction in acidic conditions. In basic solution, if it were to occur in basic solution, again, the question would specify whether it's in acidic or basic solution. We're going to add hydroxide ions to both sides and then convert those into waters, cancel any extra waters. So I've got 2 hydronium H ions. I'll add 2 hydroxide ions over here and 2 hydroxide ions over here. So then I have Cl2 plus H2O plus 2 hydroxide ions converts into chloride, hypochlorite, 2 H plus, and then those 2 hydroxide ions. Now those 2 hydroxide ions, they should combine together and give me 2 water molecules. And then we go through here and say cancel any extra water molecules. So I started with 1 molecule of water and I ended with 2 molecules of water. So one of these water molecules just hung around and didn't do anything. So I can cancel out this guy and then cancel out one of them here. So now my net balanced reaction is chlorine plus 2 hydroxides going to the chloride ion, the hypochlorite ion, and water. So this is what it would be in a basic solution. And there's that, and what it would be in acidic solution. So what do I want to say about, let me recap here and just summarize what I want to say about balancing redox reactions. It's very tedious, and really there's nothing insightful to gain about it other than knowing how to do it, and the key principles behind it, which is that you should have conservation of mass. You should have the same number of atoms and elements on one side as you do on the product side, or rather the reactant side and the product side, and you should also have conservation of charge, conservation of electrons. So that's why we have all of these special cases. You will frequently see that a lot of these steps are unnecessary. If you have no chemical species that have oxygens in them, well, then you don't need to add any water molecules to balance the hydrogens and the oxygens. You will frequently only need to worry about making sure you have the correct number of electrons in your redox, in your 2 half reactions. So there's that. So if people have questions about this, I would be happy to discuss them. I'm not going to really harp or assess people on their ability to balance redox reactions, but it can be a little bit helpful if you're having a little bit of trouble working through half reactions, identifying the appropriate half reactions for a redox reaction. So if you have any questions about this, I would be very happy to discuss them in office hours. But like I said, I'm not going to assess too much. I'm never going to give you guys something explicitly like this, where I just say, given an unbalanced reaction, what is the balanced chemical reaction in acidic or basic solution? I'm not going to ask people to do that, but there's still a little bit of insight to be had during the course of the argument. Identifying half reactions, making sure that you have a balance of mass as well as a balance of charge. And just making sure that you also are transferring the correct number of electrons in each of your half reactions. So other than that, that's it for this video. If you have any questions, I would be happy to answer them in office hours. Otherwise, I will see folks later.